process. Sounds familiar, but you can't believe it. It's not what you think. So if somebody tell you Gaussian process, what you gonna come in your mind? What you gonna get in first thing that come to your mind? Yes.
Like a normal distribution.
Normal distribution. Normal distribution, but it has process on it. Gaussian process. We are talking about random processes, and with Markov processes, and we went to the frequency domain to study that. And yeah, normal. That's correct. That's coming to our mind because normal distribution is very famous. So first thing that coming to mind, oh, there is normal distribution somewhere inside. But another thing that coming to your mind, anything else coming to your mind? Process. The other thing that coming to your mind is a process. And we talk about process, and we said, okay, about process, we talked a couple of sessions, I think 3 sessions we talked about, no more, maybe 2, 5, about the random process. Okay, so let's break that down a little bit. So we talk about random variable x. We said random variable, it has distribution. And we said random vector, we add more x, y, x dot, y dot, for example. Random vector. Oh, this is vector. This is random variable. And then we said, what about make it random process? So in random process, we put one t here. Dot means the velocity, for example, another derivative. But right now we are talking about Gaussian process. Q. Process. It should be process, but it's not just process. It's another maybe dimension higher. Instead of t, we want to say anything, input. Instead of t, we want to use input. So it means it's another process, but it's not just t. It can be t too, but it can be anything inside. So it can be u as an input. Like we have x of u, y of u. It can be a space too. Doesn't need to be just time. And can be time and a space. That's another thing. It's called a spatial temporal Gaussian process. U is a space, for example, x dot u. We have Gaussian process for decades, for a long time, but it wasn't this much studied like right now. They were used that in geostatistics for modeling, for example, weather modeling, anything spatial, anything related to spatial things, they use Gaussian process. Probably you see the pictures of, for example, they want to show the weather, how weather changing, how wind changing, in news, for example, you can say they are all Gaussian process. But in 2009, I think, or 2006 actually, the first book came out from Gaussian process in machine learning. And that was application of Gaussian process in machine learning, and that was amazing. The first guy, Carl Rasmussen, I hope I pronounce it right. Carl Rasmussen is and Chris William, and then Neil Lawrence. Neil Lawrence was actually the guy that makes me interested to Gaussian process, and I did my thesis in Gaussian process, my PhD thesis. I use Gaussian process for modeling lane marking, correlation between lane marking in autonomous cars. And that was impressive. I actually emailed Neil Lawrence and asked him, and in that time he was in, I think, in Berkeley, or I don't know. Right now he get out of school, and right now he's in Amazon managing AI things in Amazon, supply changing. But he is amazing. You can find his videos in YouTube, all around the YouTube, and he's just talking about Gaussian process, and he's thinking that Gaussian process can change everything, even can be better than neural network, and it is, because Gaussian process doesn't have overfitting that we have in neural network a lot because of lots of data, and sometimes it's too much, and model even learn noise from data. Whatever is in the data, we learn it. It's not supposed to, because learning is noisy by itself. We need to learn patterns, not data. And this is the place that actually Gaussian process come in, and Gaussian process makes everything explainable. You can do amazing things. Whatever you are doing with neural network, you can do with Gaussian process. But we're not going to go that deep in this class. We're just going to introduce a Gaussian process as a function optimization method. So Gaussian process bring function. When you are bringing input as a U or input, this becomes function. T was function too, but this can be function of everything. Function. So we are moving to actually introducing uncertainty in function space. This is what we are doing here. Uncertainty in function state. Maybe you say what that means. Function is, in function, you have some index. Like for example, you're saying f of x. X is index. Okay, it can be one dimension, it can be two dimensions, it can be three dimensions, it can be n dimension. Doesn't matter. It has it can be lots of inputs. That's index. And in one dimension, it's something like that as a signal. So another difference between random process and Gaussian process is that random process was just time one dimension. We don't have two t1 and t2, just have t one time, at least in this universe. Maybe we have different time in different universe. Of course we have. And but in this universe we just have one time. But imagine we have different x's. If it's one, so imagine this is a function, f of x. We knew function. Function is when we put one value for x, you get one value for f of x. Okay? But what means by uncertainty of the function? Uncertainty of function means we have some things around this function. But when it's Gaussian, it's so beautiful, nice, and smooth. That means uncertainty in a function. And Gaussian process let us to have this one. In one dimension is like that. In 2 dimension, gonna be a 3 dimension. It's gonna be amazing. Anyway, we can see that. We can see the pictures, and they are impressive. That's what we want to talk. We want to talk about Gaussian process. Even though it's called Gaussian, it's supposed to be everything Gaussian, but it's not really everything Gaussian. Some stuff can be changed. I'm going to talk about that. That's the beautiful shape. You can make that. I made a couple of them in this slide. So Gaussian process, or GP, treats function as a random function. So we have distribution, Gaussian distribution over functions. That's great. We have distribution over functions. As you can see in this picture, for example, in this picture, we have a couple of points. This picture is a regression problem. Regression means you want to fill it. You want to find a function. You have a couple of points of that function, and you want to find the rest. When I'm talking about function, it's really mathematical function. It's not points. It's mathematical function. From those points, from those samples, you want to find exact function. Like f of x is x e power, for example, theta. That's function. That's why it's so beautiful. Okay, so this is regression. So we want to find what is the best function that passing these points. When the points are closer, this uncertainty is less. When the points are far, as you can see, these 2 points are far, this uncertainty here increasing. So it means you can have multiple functions that passing that. So this multiple function make a space of uncertainty. And when you go far, as you can see here, there is no more observation coming, or more test points coming, and this is increasing and increasing. But increasing in a way that Gaussian increasing, smoothly. Good. So this is the big picture of Gaussian process. So Gaussian process introduced with 2 values, mean and what? You are just waiting till I tell you covariance or variance, but I'm not saying covariance. I'm gonna say kernel. But the same. Kernel act like a covariance, or even not covariance, autocorrelation actually. It acts as an autocorrelation. Let I choose another color. That color is not. So this is kernel. Kernel is like autocorrelation. Why is like autocorrelation? Because between 2 x's, 2 points of that x, like in autocorrelation, we had, if you remember, we had autocorrelation of x tau was expected value of xt plus tau, remember? This was autocorrelation. 1x different time. But kernel is also between 2 points of that function. 2 points, 2 index. Those are index. We call them index. They are not time anymore. We can call them input or index. Indexes. So that's why I'm saying it's not just Gaussian, because that kernel is acting like autocorrelation, but can have different function. K can be different function. If K be similar to Gaussian, the shape is so smooth. Like in this one, K is actually exponential. If be exponential, it's going to be a smooth. But it's not always exponential. It can be linear. If be linear, this shape going to be more like a line. If be, for example, we can have different kernels. And that's why we add lots of power to Gaussian process. We are moving more than just Gaussianity or Gaussian. We are not limited to Gaussian. Okay, so let's clean this up. What else? So this mean is the mean of all of these functions, and this kernel is actually a specified relationship between two indexes in that function. We're going to talk about that. What that means, it means we have a set of functions. As you can see in this picture, I draw like 3 of them, the blue, red, and green, and black too maybe. Yeah, is black too? Yes. No, it's not black. And these functions actually jointly following Gaussian distribution. They are jointly like acting as a multivariant Gaussian distribution. Okay. So right now we know what is the difference between Gaussian process and random process. In random process, we just had time, but here we can have anything. We can have space and time. We can have just a space. We can have, if we put it just time, we're going to change it to the random process. But we are giving more flexibility to that. But most of things, at least these relationships between these functions is Gaussian. This is the main point. They are joint Gaussian. They are jointly Gaussian, these functions. And this allows us to express uncertainty over entire function. It's like that. Look at that. That's uncertainty. When we have that gray area, specify how this function can change. So it can actually model uncertainty. Okay. So let's go for definition of Gaussian process. The Gaussian process is fully explained by mean and covariance. It's normal. In Gaussian process, we always had that. In Gaussian random variables, we also had that. In Gaussian vectors, we also had that. This is very similar to Gaussian vectors. We can see later. And mean is the mean function. And covariance is actually kernel, but it's not actually covariance, it's autocorrelation. But they call it covariance too. Doesn't matter. So the kernel also called covariance in Gaussian process, in GP. So, but what is kernel? Kernel is actually the main point of Gaussian process. Kernel specify relationship between indexes, between inputs, between x's, for example. We have different type of kernels, and these different type of kernels you can do with different application. You can use that for different application. The main one that you use a lot is a squared exponential or radial basic function, radial radial basic function. I don't know why it's called radial basic function, but it is actually exponential. Look at that, it's very similar to Gaussian. So specify how x and x1 changing. What you can get from this kernel. What you can get from kernel. You know, in Gaussian shape, this is like Gaussian shape. But here we had x minus mu, for example, in Gaussian. Here we have x minus x prime. But we also have norm here that is actually Euclidean distance. This is not Mahal distance, this is Euclidean distance. A squared of Euclidean distance. So it's showing normal distribution was like this. It's showing when x and y, this is 0. X minus x prime. If x minus x prime going to 0, this probability getting higher. And what is this probability? Covariance. So it means they are more correlated. And makes sense. When the position of the robot is very close to the next position of the robot, they are very correlated. That's normal. Because it's following Gaussian. So this kind of kernel showing when 2 points or 2 index are very close, they are more correlated. Very makes sense. This is called a squared exponential. Because it's squared. Because we are squaring this difference, we are kind of giving more, we penalize it. We are exaggerated. Okay, that's the first one. If we draw the picture of that, it's going to be something like that. The picture is like this. This picture showing when x and x1 are equal, when they are in diagonal, the intensity higher. Makes sense. This picture is like a 3D picture. If you turn it up, it has like this. I can draw it like these colors showing intensity. This is like this. Maybe another color. Anyway. This was the first one, and the main kernel. This is the main kernel. We have another kernel. We have linear kernel too. Linear kernel is just dot product of x and y. It means when x and y are equal, almost equal, they have more power. When they are when they have more power, when they are more equal. Similarity actually. When the similarity grows, the product is actually showing that. As you can see, when the product, when the similarity grows in this area and this area, they are getting close. They are getting close. So they have more correlation. Okay, that was good. Another one. We have periodic too. In periodic, of course, we have sine and or cosine here. And still we have magnitude of x minus x, because we need to show difference between x and x prime. But if we have sine or cosine, it's going to be like periodic. Periodic is like that. I draw it here. or maybe if I choose another yellow color, you can see that it's going to be like that, like a sign. In 3D is like this. So these kernels show so many things. And like, for example, this kernel, the last one, periodic one, can be used, I use that for tracking shape of the targets. Like, for example, you want to follow the shape of the human. Imagine the shape is like that. And you want to track it. When I'm saying you want to track it, why this is periodic? Because you can model it with some values, that this value, if you draw it, is going to be like this. Similar is not all equal. And when I'm talking about tracking, means estimating. Next, like for example, this human walking, and going behind a wall. And you still want to, you can see that, but still you want to see where is that, estimate the position. All right, this is so complicated. And this shape need to be convex to do that. This is not really convex. But I want to just tell you the application. Lots of application. That's the definition of Gaussian process and kernels. Let's see some applications. Oh, why it show like this? Okay, let I show all of it. The first application is regression. Regression means actually you have some points, some given data. First of all, Gaussian process is kind of supervised methods. You know, in estimation or in perception or machine learning, you have some data that's called training data. This training data labeled. When I'm talking about labeled, it means somebody mentioned, for example, specified this data is, for example, cat, this is dog, this is bird, for example. So somebody labeled this, if it's classification, for example. This data called labeled data. So if you want to train a model for supervised learning, you need to have some training data. This training data divided by 3 parts. So you have training data, you have labeled data. Labeled data. One part you use them as a training. One part you use them as a testing. One part you're using as a validating. So you divide labeled data to 3 parts. Because when you train model with some training data, you don't want to test it with that again, because testing means you try the model with something new that you haven't seen, the model haven't seen that before. So that's why we need to have training and testing. Why need to be labeled? Because we want to see how off we are. So we need to have labeled to check it out, what we detected and what is reality, to find, for example, least square, to choose how bad was our estimation. What is validation? Anything coming to your mind? What is validating data? Okay, validating data is for parameters. We call them hyperparameters. Here, when I was talking about kernel, let I come back for kernel a little bit. I just need to show you that. Here we had some parameters, I forgot to talk about them, like these two. They are parameters. But these parameters are not just normal parameters that you tune them in action. You learn them. You learn them from validation data. So the validation data is for these variables. These variables called hyperparameters. These parameters called hyperparameters. In machine learning, we have them a lot. Hyperparameters. Okay. So here we also have hyperparameters. Hyperparameters coming from validation data. But what is relation with regression? So in regression, we have some training data. For example, we have some training data, and we want to find a function that completes those data. That's called regression. So we are looking for a function, this f of xi. But this function has some noise on it, and this noise is Gaussian. We assume Gaussian because it's Gaussian process. So we assume this noise in this training data that is labeled is Gaussian. It's labeled means it's in the curve. For example, you are looking for this function, and I'm saying is labeled means that they are already there. They are not off. Or they are close to that. Maybe they're not exactly there, because there is some noise too. I want to say they are not false alarm. They are not outliers. They just have little noise, because they are labeled. Somebody did that, but still they have some little noise, that this noise is here and it's Gaussian. So, and you want to find this function. This function is what we want, f of x. But this function follows a Gaussian process. When you mention GP means Gaussian process. What else about this? What other prior we know about this function? So we have those points. They are training data. That's good. We want to find the function, but we have another prior. What is that? You tell me. What other prior we have in this function, in this line, red line that I mentioned? Is any other prior? What prior means?
Like before.
Prior information. What prior information means? Information that we knew before. Yes. Information that the assumption. Something like assumption. So this kernel is another assumption. So the kernel is another assumption. So based off this assumption, that is a prior information, and those given data, we want to find posterior density. Okay, I think it's not time. We can finish that next class. But that's the main part. We want to find posterior density. We can talk about that next class with more details. Any questions? Okay, so see you Monday.